Welcome to Jom Studylah YouTube channel. Let me share with you today's presentation on carbonyl compound. And in this presentation, we will explore its structure, properties, and significance in organic chemistry. Without further ado, let's get started. Carbonyl compound. For the introduction and specific compound to be discussed in this topic include naming of aldehyde and ketone, and draw the structure and name the compound according to IUPAC nomenclature and common name. On top of that, you also need to know about the functional group. For carbonyl is C equal O, and the general formula is CnH2NO, and is focusing on aldehyde and ketones, where you already know that aldehyde and ketone are isomeric. Carbonyl compounds are polar, and in general, aldehyde is more reactive than ketone toward nucleophilic addition reaction. And just to add a little bit about the background about the aldehyde, it's also used in the textile and leather industry, and also used in a plastic and resin. Let's go detail about naming and knowing the aldehyde further. In terms of the naming of aldehyde, first you need to identify the longest carbon change that include the dash CHO, which is aldehyde group, and this change form the base name of the compound. And then you have to replace the dash E ending of the corresponding alkane with dash AL. Example, methane become methanol, ethane become ethanol, propane become propanol, and then you need to number the change starting from the carbon in the dash CHO group, and the carbon of the aldehyde group is always carbon number 1, which is we would specify it as C-1. Example, ethanol. Step 1, the longest change consists of 2 carbon, and base name is ethane. And step 2, you need to replace the minus E with dash AL. So for example, ethane become ethanol, and the structures as shown here, which represents CH3 and CHO. Example 2, let's look into the 3-methylbutanol. Step 1, the longest change containing CHO, which is consisting of 4 carbon, and the base name is butane. And then you need to replace dash E with dash AL. For example, butane becomes butanol. And the step 3, you have to number from dash CHO as carbon 1. And the step 4, a methyl, the CH3 is a group is attached to the carbon 3. And the structure's name as shown here, where the name is 3-methylbutanol. So below here, there is some example regarding the aldehyde, where methane, so in terms of the aldehyde, naming, it becomes methanol, and the formula is HCHO. Ethane, ethanol, we already explained just now. The formula is CH3CHO, and propane become propanol, and the formula is CH3CH2CHO, and butane become butanol, and the formula is CH3CH2CH2 and CHO. Let's look into the naming convention or naming of ketone. Replace the dash E ending of the corresponding alkane with dash O and E. For example, methane become methanol, and ethane become ethanol, and propane becomes propanol. So when naming a ketone, choose the longest carbon change that contains the carbonyl group, which is C equals to O. So number the chain so that the carbon atom in the carbonyl group gets the smallest possible number. Example, propanol, which is acetone, the carbonyl group is on the middle carbon of a 3' carbon change. For example, CH3-CO-CH3. So the carbonyl carbon is carbon 2. So the name is propane-2-1. So commonly called propanol. And butanol, so the carbonyl group is on the second carbon of a 4 carbon change. So CH3-CO-CH2-CH3, where the carbonyl carbon is carbon 2, and so the name is butane, butan-2-1, and commonly called butanol. And this is a few examples of naming of ketone. So this is the structure on the left-hand side. So the name is propanol. So the name for the general name is acetone. And we have a sample for butanol and also 2-pentanol. And let's look into the reactions of carbonic compound. So we have two here. One is the reduction of aldehyde and ketone. And secondly, we have this nucleophilic addition, reactions of aldehyde and ketone. For the reductions mean adding hydrogen or removing oxygen to the carbonyl group and converting it into an alcohol. The reagent and their effect, we have example here, where the use of lithium aluminum hydride or sodium borohydride, and the end product performed is the primary alcohol ketone and also secondary become a secondary alcohol. Example reactions we have as shown here, where we have the reactions of the sodium borohydride and also the lithium aluminum hydrates. And then secondly, we have the reagent of catalyst hydrogenation, and the reaction type is the hydrogen addition across C equals to O, and the product forms is aldehyde primary alcohol, and also we have ketone secondary alcohols. And in the reactions of nucleophilic addition reactions of aldehyde and ketone, where aldehyde and ketones undergo nucleophilic addition because the carbonyl carbon is electrophilic beta plus and the oxygen is nucleophilic beta negative. So nucleophilic attack the carbonyl carbon that breaks the C equals to oxygen pi bond, and the oxygen become negatively charged and then prototinate to form an alcohol or related product. So we can see here with the use of nucleophilic reagent, the reaction type is the first one, we have a reduction where the product form is alcohol. The second type is cyanohydrin formation, where the product forms is the COHCN group. And then we have the reaction type when we use the ROH, which is acid catalyst, where acetyl formation, and also there is a product form, and also we have the condensation reactions where the product form is oxime or hydrazone, and finally we have the additions of R negative group where alcohol after hydrolysis. And the key point here is aldehydes are generally more reactive than ketone, and the less steric hydrants and less first effect. So both undergo reduction and nucleophilic additions via attack at the carbonyl carbon. And the last one, we have the iodoform reaction. The iodoform reaction is a chemical test used to identify compounds containing a methyl group adjacent to the carbonyl group that is COCH3. And it's also work for certain secondary alcohol that can be oxidized to such a carbonyl compound. So the reaction produces a yellow precipitate of iodoform, and which has the characteristic antiseptic odor. And the structural requirement is a compound give a positive iodoform test if it contains the group of dash COCH3 or can be oxidized to form one, meaning that is methyl which is acetone. And then we have a secondary alcohol with a structure of CH3-CH, where negative R are iodoform positive. And then in terms of the reaction step, in terms of the carbonyl carbon, let's consider a methyl ketone like acetone, CH3-CO and CH3, the chemical formula. So halogenation at the alpha carbon, where the carbonyl carbon increases the acidity of the alpha hydrogen, where the hydrogens on the carbon next to the carbonyl. And in the basic solution, one of these hydrogen is removed by a basic like OH negative, forming an enolate ion. So the enolate then react with iodine to substitute one hydrogen with iodine, and this happens repeatedly until the methyl group is converted to Cl3. So, CH3-CO-Ri2 based on Cl3-CO-CRSO, the carbonyl carbon stay part of the carbonyl, but the adjacent of alpha carbon become triodomethyl. And then we have the process of hydrolysis, where the base OH then attack the carbonyl carbon, where in the process of nucleophilic attack, causing cleavage of the C-C bond between the carbonyl carbon and the triodomethyl carbon. And the product forms, at the end of the product, iodoforms, the yellow precipitate is formed, and also a carboxylate anion derived from the carbonyl carbon. And then we have the key role of the carbonyl carbon in this situation is where the carbonyl carbon makes the alpha hydrogen more acidic due to resonance stabilization of the enolate, and it's also precipitate in the CC carbon cleavage in the final step, forming the carboxylate product. So while the halogenation happens at the alpha carbon, the carbonyl carbon is crucial for activating alpha hydrogen and undergoing nucleophilic attack and cleavage in the final step. And as a summary, during the enolate formation, so the involvement of carbonyl carbon is to stabilize the enolate ion, and in the step of iodination, where the involvement of carbonyl carbon is at the alpha carbon due to carbonyl activation. And at the step of cleavage, nucleophilic attack the carbonyl carbon, which is causes CC bond breaking. And where during the product formation, carbonyl carbon become part of the carbonyl ion. That's all that we have in today's presentation. Please subscribe to Jom Study YouTube channel. Wish you all the best in your study. Thank you very much.